Today is the last session of the live session for the optimization and fundamentals course, and what was discussed in the week 12 was the dynamic uh, programming algorithm, its application to the inventory control problem, and um, the, the principle of optimality in dynamic programming, and in general, the optimal control for a system with linear state dynamics and a quadratic cost function. So I think Professor Kulkarni is from the Systems and Control department at IIT Bombay. So I guess that's why he has included this subject is also into the optimization course. So we'll discuss some problems from this. So basically, in optimal control, you are sort of solving a sequential decision making problem where at each each time step you need to take an action, and overall you want to choose action such that you want to optimize some cost over your time horizon. Okay, and uh, you have some notion of the dynamics of the system, how the system evolves with from each time period to time period, and how the actions change that, and dynamic programming is an sort of approach and an algorithm to find the optimal actions for such a problem given certain nature of the dynamics, certain given some knowledge uh, and the nature of the about the nature of the dynamics. Okay, so we solve this first problem, which is from an assignment given last year. So you have this inventory control model. There is some shop, a tire selling shop called JK Tires, and it needs to decide the number of tires that they want to order over some periods from 0 to n. So you have n periods. This could be like every month, how much tires do you need to order to keep in the shop, the stock that you need to keep. So you have this variable xk, which is the number of tires that you have in the shop at each period k, at the beginning of each period, like at the beginning of each month, you can say. Uk is the number of tires at time period k. So for a given month, how many more tires are you going to order to meet the demand of that month? And wk is the demand that you are going to get in time period k. So this is sort of stochastic. The demand would come randomly at each time period. The number of tires that the JK tires has at the beginning of time period k plus 1 is given by xk plus 1 equal to max of xk plus uk minus wk. So this is the how the system is evolving. In the next month, your stock will be equal to uh, whatever is your stock at the current month plus whatever you have ordered in this month minus the demand. So this is the how what will be the stock at the next month. So because this can be negative, but you can't have a negative stock. You can't sell more than what you have. This is what you have, and this is what you're able to sell because of the demand. So you will take this max. So this is if your demand is more than what you have, that is xk plus uk, then this value will be negative. So xk plus 1 will become 0, so you'll have 0 stock in the next month if your demand is more than what you are able to stock up. So yeah, so wk is a random but independent of each other. That is, your demand is random and independent, and they are asking us to assume that at each period we can only add more stock to our shop. We can't remove any stock from our shop. So uk is greater than 0, and at any time period you can only store maximum of m tires. So that is the capacity of our shop. We can't have more than m tires. And if you have xk tires at time period k, then at most m minus xk tires can be ordered at any time period, because at any time period you have a total of xk plus uk, and that can't exceed mk. And so you have costs associated with your components. So holding cost is r of xk, which is linear in xk. That is to eh, hold those tires in your shop. To keep those tires, you have some certain costs, like maintenance of your shop and things like that, maintenance of the racks or boxes. Okay. So that is your holding cost, which is r of xk. Ordering cost is the cost of purchasing more tires to stock to keep, to increase your stock, to meet your demands at each time period. So that is c of uk. That is also linear in this uk. So for each time period k, the sum of holding cost and ordering cost is your stage wise cost. Like at each time period, at each stage, you have a cost of r of xk plus c of uk. And then you have a terminal cost, which is defined as capital R of x capital N is equal to gxn. So this is like at the end of your n periods, whatever stock is left, that is xn. At the last time period, whatever stock you have left, you have a cost on that r of xn. Okay. So let's look at some question. So this question is asking if GK tire has a shop capacity of maximum 10,000 tires, and if P is equal to 100, then what values of ordering costs are not possible at any time K? So shop capacity is 10,000 tires. That means this value M is equal to 10,000. So M is equal to 10,000 means at any time your shop can have only 10,000 tires, right? So what values of ordering costs are not possible at any time k? So ordering cost is c of uk is equal to p of uk, and p is given to be 100, so it is 100 times uk, and your xk is will also be greater than equal to 0 and between 10,000. So that means your uk is also between 10,000 and 0. Okay, so that means this cost, uh, which is equal to 100 times UK, will be between 100 into 10,000 and 0. So it will be between 100 into 10,000 and 0. So you can see this A is between, so this is possible. So you can say possible. This is 101 into 10,000. So this will be greater than 100 times UK max, that's 10,000. So this is not possible. Not possible. So here also it is 10,000 into 101, which is same thing, I guess. So not possible. And this is possible. So option B and C are not possible at any time. Okay. So that's a simple question. And so let's look at this question. If initially JK Tires has 200 tires in the shop, then after n equal to 35 time periods, the optimal cost J star x naught using the dynamic programming equations is given by. So for this we need an idea of what is the dynamic programming equation and what is this cost, for which we need to find the optimal value, and what does it have to do with the initial number of tires in the shop and the time period n equal to 35. Okay, so initially there are 200 tires, means x0 is equal to 200, and the cost that is optimized is so the cost that you incur is r of xn, which is at the terminal. You can say, like, if you start from some x naught, then the cost you occur is rxn, which is the terminal cost. You can say this is the expected cost, rxn plus summation k equal to 0 to n minus 1, or other costs that are what, r of xk plus c of uk. Okay, and something of pasted here. Okay, this is the cost that you want to minimize, or I can call this, okay, this is the total cost actually. Okay, So in the dynamic programming, what you want to solve is you consider uh, jk xk as the value function at time k, or the cost to go from time k, and you can call this the optimal. And this is defined via the dynamic programming equation as r of xk plus minimize uk. So this is your decision variable. It is how much to order. Plus expected value of jk xk plus uk minus, or you can write this as max of xk plus uk minus wk comma 0. Okay, so we say this is jk plus 1. Okay, so this is basically jk plus 1 of xk plus 1. So xk plus 1 is max of this value. So from state xk plus 1, what is the optimal path to go, optimal cost to go? That is this. You take the expected value of that and you take this min from the like the cost you ordered, because that also depends on uk, and this jk also depends on uk because xk plus 1 depends on uk. So you minimize over uk plus the holding cost that only depends on the current state xk. So you get this. So if you take the boundary condition, it is jn is equal to gn of xn. So using this boundary condition, so for different xn values you can get what jn is. So here it is capital Rn, actually capital Rn of xn, which is g of xn. So you can get jn of xn for different xn values, and then you can, from jn you can compute jn minus 1 for different xn minus 1 values, and you can keep backtracking it till you find j0 x0, and you only need to find j0 x0 for x0 equal to 200, which is given here. So your optimal cost from x0 will be, which is j star x0 will be equal to j0 200. That is your C option. J35 200 will give us G times 200, and J35 0 will directly give us 0. So that won't depend on any of the previous whatever you did in n-1 periods. Okay. So this is this question. Let's look at this question where you have a different model. So you have the system xk plus 1 equal to xk plus uk plus wk. So this is how the system is evolving. This is not exactly like the inventory control problem where you had xk plus uk minus wk, but here you have xk plus uk plus wk, and uk is some sort of control applied to this system which is linearly evolving, and wk's are random variables with mean equal to 0 and bounded variance, and we want to find some policy pi star to minimize the cost of this form. This is like a quadratic cost. It is quadratic in your decision variables uk and also in x case the state variable. So the optimal control at any time period is what? The optimal control is the u star k, whether it is linear or quadratic, or linear in x or quadratic in x. That is what is asked. So this was discussed in the lectures that if you have a linear system with linear dynamics, akxk plus bk uk plus wk, and your cost is quadratic, that is x and xn transpose qn xn plus summation k equal to 0 to n minus 1 x transpose qk xk plus uk transpose rk uk, and q is symmetric and positive semi-definite, and rk is symmetric and positive definite, and And if you have these conditions on wk just given in this question, less than infinity, so then your optimal control is linear. So how you get this is you write your optimal like your dp equation for the above problem. So one thing you can check is q is symmetric here, because q is here actually identity, right? It is identity or 1 basically, because it's not really a vector, it's a scalar. And r is also identity, so they are both symmetric and you can say positive definite. So it's like a 1 cross 1 matrix, just positive. And these two conditions are also given. So as was proven in the lecture, the optimal control for this is linear. So you can say it is linear in xk. So how it was shown was, first the optimality equations for xn was like n minus 1 period was written. So you will get a quadratic in your xn and un minus 1. It will be some expected value of xn minus 1 transpose qn minus 1 xn minus 1 and un minus 1 transpose rn some un minus 1 and some other terms. And the expectation over wk terms you will have, those terms you can make it go to 0. And so those you will get by expanding the definition of xn. And then you will have the remaining terms for which you can, because it's a quadratic, you can take the gradient and set it to 0, gradient with respect to un minus 1 and set it to 0, and that will result in a linear equation, un minus 1 star equal to minus. So this I am directly writing from the notes. So as you can see, it is linear in xn minus 1. And then you do the same thing for jn minus 2, you'll again get linear in xn minus 2. So if you keep doing, then for some k, you will get something of this form, where you have this lk defined as minus vk transpose, this capital K. Okay, write it a bit neatly. And this k is also defined in some form. Vk transpose. So it's a bunch of equations. Okay, so this is the k, capital K, that is used here, and this is the boundary value of this. This is called the Riccati equation. So the main point is this u star k is linear in xk, and this lk is defined by all these terms, q and qk, rk and everything. At here you can see this q is not dependent on k, q is same throughout. For all k it is identity. Same as the case ak, bk are both 1 for all k. So it is linear in xk, not linear in k, not quadratic in k, not quadratic in xk, it is linear. So the question is, suppose the state at time period n minus 1 is xn minus 1 equal to 3. What is the optimal control at n minus 1? So we need u star n minus 1. So that will be defined in terms of this lkxk. So xk we know is n minus 1 xn minus 1. So it is ln minus 1 into 3, and we need what is ln minus 1. So Ln minus 1 will be this whole thing, and here if you see, this is k of small k plus 1, which is k of capital N. K of capital N is equal to Qn, and Qn is equal to 1. We know bk is 1 from here. Rk is also Rk is also 1. So this is 1 plus 1, it is 2 inverse, so that is minus half. These bk, ak, and these all are 1. So L minus 1 is basically minus half, isn't it? So u star n minus 1 is equal to 3 into minus half is equal to minus 3 watt, which is P. Okay. You have any doubts on this? Skandan, you have joined, right?
Yes. Yeah, I don't have it.
Sorry?
Yeah, am I audible?
Your voice is not little. If you have any doubts, then you ask, or you can type in the chat also, or you can interrupt me and ask if there is any doubt in anything. There is some background noise in the chat, so
Okay. Yeah, I don't have any doubts.
that's good. Okay, so this question is, suppose the system starts at x naught equal to 1 and n is equal to 2, that is, there are only 2 time periods. What is the optimal control at time k equal to 0? So we just need to find u0 star. So u0 star, like uk is of this form, and here you have lk of this form. So basically you need to find all these k in some form. So if I substitute all these as 1, then what I get is like ak is 1, bk is 1, rk is 1, all this is 1. So k is equal to k plus 1 minus k plus 1 into this is 1, this is 1, this is plus, let me check. Yeah, so this is k plus 1 plus 1 inverse into k plus 1 plus 1. So this is equal to k plus 1 minus k plus 1 square. Okay, the whole thing is okay. plus 1. So we have K2 is equal to Q2 is equal to 1. K1 will be equal to 1 minus 1 by 2 plus 1, that is 2 minus 1 by 2, that is 3 by 2, and K0, this will be equal to 3 by 2 minus 9 by 4 upon 3 by 2 plus 1, which is 5 by 2 plus 1. So we cancel 3 by 2 minus, I'm sorry, 9 by 10, right, plus 1. Okay, is this correct? One upon 1 plus 6 by 10. Where is it 6 by 10? Here, this part. 15 minus 9 is 6 I. 6 by 10 correctly. Thanks. Comes 3 by 5. This is 8 by 5. Yeah, so this will be 1.6. Yeah, thanks, that is correct. And this is 1.5. So this U star is basically 1 upon K0 plus 1 into K0, right? Sorry, this is LK, L0. Minus of this. I think it is dependent on K plus 1. So it should be K1. So we don't need to compute K0, I guess. right? Because LK is dependent on capital K subscript K plus 1. If I'm not wrong. So then what do we have? I think here it should be K. I think here it is K only, not K plus 1. It is K only. LK is equal to, wait, I'm slightly confused whether it is, then my roads are written. Okay, maybe it's K plus 1 only. Just check it once. So then this is K1, K1, and this will be minus 1.5 upon 2.5. It is like 3 by 2 upon 5 by 2. It is 3 by minus 3 by 5. Which is how much? Which is 0.6. But here the option is 0.62. So if I take okay, so this is 0.6 and I have one more term, right? I need to find U star, which is N0 into X0. Okay, X0 is 1. So this will be 0.6 only, minus 0.6. It is K plus 1 you are saying, right? Yeah, that is what we reused. So we're getting 0.6 and 0.62. Once let me check in the textbook dynamic programming. I have the textbook. This is this quadratic part, right? So I have nk is in terms of, yeah, it's k plus 1 only. Yeah, so what we did is correct. It's in terms of k plus 1 only. So maybe the option is not right. It's point 0.6. It's coming exactly point 0.6, right? So this is point 0.6. There is not 2. Okay. So let's look at the last question where they're saying this variance is equal to 1 for any k and n is equal to 2. What is the optimal cost if the system starts at x not equal to 1? So optimal cost was, I just reuse the definition what was written in the lecture notes. X naught transpose k naught x naught summation k equal to 0 to n minus 1, expected value of wk transpose. So you have x naught is your 1, k naught is 1.6 into 1 plus summation k to 0 to n minus 1 is 1 actually. This wk k, you can write this like this. So it is 1.6 plus expectation is also there here. So this k you can take out. K is 0, expected value of wk square plus k1, expected value of w0 square and w1 square. So this is 1.6 plus this term is given as 1 and k0 is 1.6 and k1 is 1 1.5. So this is I get 4.7. Okay, so this answer is 4.7. So just we had to identify that these all values turn out to be 1, most of the values q, r, p, capital A, and then it turns out to be quite simple, but we also need to be aware of what are these formulas, and if we have written them correctly in the notes, then It's easy to just substitute it into them, and we can verify it from the book if we have written it wrongly. And if we don't know the formula, then we'll have to derive it and arrive at it, taking the gradient and minimizing the expectation, knowing that the expected value of w is 0, and things the way it was discussed in the lecture. Okay, so I'll discuss one more question. So we have this dynamical system, xk plus 1 equal to wk plus auk. Initial state is x naught equal to minus 1. The cost function is of this form, and wk takes the values 0 and 1 if xk greater than 0. Both values have equal probability, and if xk is less than 0, the disturbance wk is 0 with probability 1. The control uk is constrained by this. So here if you see, you have these quadratics, and you can see your q and r are 1, so they are symmetric and positive definite. And I think if we also need the expectation over wk's. So wk is between 0 and 1, so the expected value will be greater than equal to 0, and if xk is greater than 0, then the expected value is 0.5. It's between 0 and 1, so that condition is not satisfied. Expected value of wk is not equal to 0. So all those equations that we used, we can't exactly use it here, so we'll have to derive and solve it. So if we look at this, we can see that the cost to go, that is j2 x2, is on this form x2 square, because there is only 2 time periods, so we can consider this. And j1 x1 is minimum u1 expected value of x1 square plus u1 square plus w1 square plus j2 x2. So this we can write as x1 square plus minimize u1 u1 square plus expected value of, so this expectation is over the random variable w1 square plus j2 of x2 we can write via this 1 minus a times w1 plus a u1 square. So we'll have two cases, because when x1 is greater than 0, like to compute this expectation, when x1 is greater than 0, w is 0 with half probability, 1 with half probability, and when xk is less than 0, wk is 0 with 1 probability. So if x1 is greater than 0, j1 x1 is equal to x1 square plus min u1 u1 square plus half into, when w1 is 1, we have 1 plus okay, so this j2 I can directly substitute it. There is no, whose x2 is this term and j2 x2 is the square of this, so it's actually this w1 plus, so if I put w1 equal to 1, I have 1 plus 1 minus a plus au1 square plus half times w1 is 0, so au1 square. So this is a quadratic equation in u1, and u1 is between u1 is given to be between 0 and 1. So this is a quadratic equation, so it can be somewhere here, or so we want to find the minima, so we can look at the derivative. It's upward opening because the coefficient of u1 square will be positive. This a is positive, the coefficient of u1 square is positive. So look at the minimum, we can set the derivative equal to 0, so the derivative of this term, I call this as f del f by del u1 is equal to 2 u1 plus 2 times 2a a square into u1. So this is your derivative, and this if I set to 0, and get u1 equal to mm, okay, this is u1, but a is greater than 0. This is what is given here. A is between 0 and 1. So if a is between 0 and 1, then implies that u1 is negative. So u1 can't be negative. So that means it is beyond the range. Whatever this minima is achieved, that is beyond 0 and 1. So it can be something like this, and this is your u, 0 and 1. So this may be where. So your minima may be somewhere here, but this is 1. So our original minima is somewhere here. That is when u is equal to 0. So this is the minimum that we want in our range. So we can substitute u equal to 0 in this, and that will be your minima. So then what we'll get is j1 x1 is equal to x1 square, plus if I substitute u1 equal to 0, and get half into 1 plus 1 minus a squared and plus 0. This is when x1 is greater than equal to 0. Okay. And you also need to solve for x1 less than 0. So from this what we get is your optimal this is equal to 0. u1 star is equal to, your policy is something like this, right? x1 is equal to 0 when x1 is greater than equal to 0. When x1 is less than 0, then what we have is wk is 0 with probability 1. So that means in this equation you can directly substitute w equal to 0. So then what you will have is j1 x1 is equal to x1 square plus w1 equal to 0 means uh, au1 squared. u1 square plus au1 square. So this is again quadratic in u1. 1 plus a square u1 square. So this is for when x is less than 0, and this is again a quadratic with like positive 75. And if you can see, the minimum of this will be at u1 equal to 0. So this will be equal to x1 squared. So this is again u1 star is equal to for x1 less than 0. Okay. So using J2, we found J1 for when x1 is greater than 0 and when x1 is less than 0. Similarly, we can using J1 we can find J0 x0, where x0 is minus 1. So x0 is minus 1 means we all need to consider the case where x1 is negative for w0, and w0 is 0 with probability 1. But x1 can be both positive or negative. So I think that can be computed in the same manner. There's nothing new in that. The same thing that we followed for J1, we have to follow for J0. Okay. You have any other doubts? Is u0 equal to 0? Yeah, I think u0 is also equal to 0. Yeah, u0 will also come out to be 0. Yeah, that is correct. Difference between UI and UI star. So UI can be like any policy. UI star is when you refer to the optimal policy. So here I was using this is U1 and this is mu. This is mu star, which is just like some policy, and mu star x1 tells you at x1 what should be your action. That action is u1 star, which in this case turned out to be 0. So it's like initially we are sure there will be no demand. At the start it is -1, x0 is negative, so there is no demand. It's not exactly demand, but the randomness is not there in this in the first stage. Final optimal cost, it comes out to be let me just increase this page. Final optimal cost, w is not always 0. W is for k equal to 1 it need not be 0, right? And depends on this a also. Like xk plus 1 has dependence on a. So are you able to solve it? Okay. So G is 0 minus 1. And this will be x0 square minimize u0. And mm, this x naught is less than 0. So this is equal to 1 plus minimize u naught. So this expectation will go and w naught will become 0. So it will be plus j1 of this. So w naught is 0 means j1 of a u naught. And u naught is positive and a is also positive. So j1 of positive is basically a u naught square, right? A is not a random variable. You can write it in terms of A only. A is some constant. So A u naught is greater than O minus A by 2. Okay, I'm also solving and just check whether that comes. So this is positive, so we need to use the positive case, which is x1 square plus this. So that is a square u naught square, that is our x1 square, plus half into this. So half plus half 1 minus a square. So this is a quadratic in u naught, and if we minimize this, we will get u 0 equal to 0. So basically you need to only minimize over this term. This is independent of u. So the minimum of this quadratic will be u 0 equal to 0. So this cost is 1 plus 1 by 2 plus 1 by 2 1 minus a square, which is basically 3 by 2 of 1 minus a square. Okay, so you made that mistake. So yeah, this is what you get, what I had written earlier. So a u naught is equal to 0 means x1 is 0 actually. When x1 is 0, you can have both. Wk can take any value, 0 or 1. So that's why you can have some different xk plus 1. So W is not always 0. Okay. So any other doubt that you have that you would like to ask? Okay. So this is the last. This was the last live session. You'll have your exam, I guess, in a few weeks. So all the best for that. Oh, it's on Sunday. So if you have some doubts, you can post in that discussion forum. Also, I try to answer if I can, or you can mail me also. I'll write my mail ID in the chat. And if you haven't been able to solve all the assignments, then it will not be very tough, I think. And you can follow some of the textbooks that I think he has mostly used this numerical optimization book by Nosender and right. In this book he has heavily referenced in many of the topics. This dynamic programming. Mm, this is for the dynamic programming part. Some part is I think from convex optimization. I think only some parts are maybe from this. Most of the things are from this numerical optimization book. Okay, so if there's no other doubt, then I'll close the session.